this is equal to omega naught L over 2. Okay. So on the other side, again, why only omega? Let's ease our problem. We just call it omega. Okay. So this is just omega L over 2. Okay. So what we have just done is we have analyzed the load distribution between A to B. So A to B, we just look into this force distribution over here. Okay. And the equivalent load is the total load under the area or under the line, which is this line over here that I'm highlighting now. So it's WL over 2. Then we have another equivalent load for the other triangle. So this equivalent load will be equal to half. The base is L over 2. And the height is also omega. So this will be equal to omega L over 4. Okay. Now, in order to find the reaction at A and at point B, you have to know the distance of the equivalent load relative to point B, for example, for this case. So what I'm going to do is I'm going to draw a line over here. Right. So the distance of the equivalent load from here to here, I'm going to write over here. So this is equal to L over 3. I will explain later during the course why is it L over 3. This is just an introduction for now. And on the other side, okay, over here, is equal to 1/3 multiplied by L over 2. So it's equal to L over 6. Okay. So the next thing we're going to do is we're going to determine the reaction. So whatever you learn in 2 P04, okay, or the static and strength of material course, do not forget, you need it a lot in this course over here, okay? So from here, we are going to determine reactions at point A and point B, okay? So we are going to carry out static analysis. Okay, we are going to carry static analysis. So we are going to do summation about moment in the Z direction, and we're going to take the moment at point B. Okay, so i.e. we take the moment at point B and summation of the moment will be equal to what? 0. Okay, so we know that the distance, okay, we are aware that the distance from here to here, we know that the distance from here to here is equal to L, right? So from here, we're going to take moment at point A, okay? So AY is going to induce a clockwise direction, so minus AY L, okay? And then so the omega L over 2 is going to induce anti-clockwise plus by omega L over 2 multiplied by L over 3, right? And then the next one is the omega L over 4 is going to be in the clockwise. So it's minus omega L over 4 multiplied by L over 6. Okay, so this is equal to 0. So we have AY L is equal to what? Trying to get my calculator now. So we will have omega L squared over 6 minus by omega L squared over 24. So from here, we know that AY is equal to 1/6 minus 1 over 24 is equal to omega L over 8. Okay. So we know AY is equal to omega L over 8. So we have to find point B now. So point B, we just do summation forces in the y direction is equal to 0. So we have omega L over 8 minus by, so it's coming down omega L over 2 minus by omega L over 4, over 4, not over 6, over 4. And then we have plus by by. The whole thing is equal to 0. So therefore, by is equal to a half plus by a quarter minus by 1/8 is equal to 5 over 8. So 5 omega L over 8. Okay. So we have all this now. So because it's positive, we know that our direction is correct. Okay, so it's positive. Right. So now we have to now work on the reaction at point A, at point B. Okay, we have to know the moment at point B, and we have to know we have to know the shear force at point B. Wait, how did we get rid of the L over 2? How did we get rid of the L over 2? Hold on. Julia, where about the L over 2 you are talking about now, Julia?
Yeah, sorry, Prof. When you were initially calculating AYL, you had L squared, and then when you got to your final answer, you just have L. I'm just wondering what happened to the squared.
Oh, okay. So what? I skip a step. You see the L over here? I brought it down, so that's why the squared got missing.
Oh, okay, cool. Thank you.
Yes, sorry, I skipped the step over there. Okay. Right. So from here we are going to find, okay, the reaction at point B, and there are a few ways of doing it. So I want to do the way that you are most familiar with, and why you're familiar with, because Dr. Koshi taught you in 2P04. Okay, so I'm going to bring the diagram down so you can see better. Okay, so now we want to find whatever that is going on at point B. Okay, and we're going to find whatever, hold on, okay, we're going to find whatever that is going on at point B. Okay, so in order to find the reaction or the shear force and the bending moment at point B, we are going to use the integration method. We're going to apply the integration method. Okay, so this is like an introduction and also a recall for all of you. Okay, so whatever we're going to form now is between point A and point B. Okay, so 0x to L. Okay, so first thing we are going to do is we're going to determine the equation. Okay, equation of the distributed load between point A and point B. Okay, so what are we trying to do over here is we are going to, so I'm going to draw a graph over here. Okay, so this is our X and this is our omega. So if this distance is our L, we know that we have this graph over here, which is omega naught. So where I just sketch, okay, so what I just sketch is I just sketch this slope over here. Okay, so we know as a function, I just call it omega. Okay, so we know that omega as a function of x, this will be equal to omega over Lx, right? So this is the equation of the distributed curve, and this is our equation number I think this might be our equation number. Okay, for this problem, it will be our equation number 3. I know we have used 1 and 2 before. So from here, using the integration method, we know that dv over dx is equal to minus omega as a function of x. So this will be equal to minus omega x over L. Okay, so this is what we call our equation number 4. So when we integrate this equation, we can get our shear force. Okay, so I'm going to zoom out. I'm going to half the page. Pardon me, just bear with me. Maybe you can take a short break while I draw half a page. Okay, here we go. So we got it now. So we know once we integrate, so let me copy this equation so you can see it. So we have this equation over here, right? So equation number 4. So when we integrate this, this is the most integration we have. So v as a function of x will be equal to minus omega x squared over 2L. Okay, omega x squared over 2L. And then we are going to plus by C1. And this is our equation number 5. So the next thing we're going to do, we're going to substitute. Okay, we're going to substitute when x is equal to 0, right? V is equal to omega L over 8. Right? Why that is the case? Because we know when x is equal to 0, right, which is at point A over here, AY we have determined over here is equal to omega L over 8 already. Okay, so yeah, we have that value. So from here, we can determine C1. So we have omega L, and we're going to substitute into equation number 5. Right, so omega L over 8 will be equal to minus omega 0 squared over 2L plus by C1. We realize that C1 is equal to omega L over 8. Okay, so now we have the shear force as a function of x is equal to minus omega x squared over 2L plus by omega L over 8. And this whole equation is equal to the dm over dx, and this is our equation 5a. Okay, so the next time we integrate again, we're going to get a moment as a function of x. So moment as a function of x is equal to minus omega x cubed over 6L plus by omega Lx over 8 plus by C2. This is our equation number 6. Okay, so from here we have to substitute another boundary condition. Okay, so we know that we know nothing about moment at this stage, but what we can be sure is when we substitute x is equal to 0, moment is equal to 0. So some of you might say, wait, why dv over dx is equal to, that is a standard formula that I'm using. Okay, Lee. Okay, it's just a formula that you will learn from 2p, that the dv over dx is equal to minus omega x, and you can find this in your textbook. Lee, does that answer your question? I mean, I can derive it, but